In this video, we're going to begin to look at water. And water is very important because all of biochemistry basically happens inside the cell, which your solvent will always be water since we live here on Earth. So key concepts for 2.1 is that water molecules are polar, they form hydrogen bonds. Ice water molecules have the maximum number of hydrogen bonds, and so they form a crystal. Liquid, they are more flexible. The attractive forces, hydrogen bonds, ionic interactions, van der Waals interactions are critical to understand for biochemistry. They basically drive everything. Like dissolves like polar and ionic substances dissolved in water. Hydrophobic effect is big when it comes to protein folding, and it's all due to entropy. Amphiphilic substances form micelles or bilayers. Molecules diffuse across membranes from regions of high concentration to low concentration, and dialysis is a important biochemistry technique for when water dissolves, and we can use that to our advantage. So we're just going to begin by looking at water itself, H2O. And water is polar, which means at the oxygen you have a partial negative charge. That's what this symbol means. And on your hydrogens you have a partial positive charge. Water is sp3, which means it forms a tetrahedral. So here's the tetrahedral right here. You have oxygen with lone pair of electrons. That's where the negative charge comes from. And you have your two hydrogens. Your hydrogens are separated by a bond angle of 104.5 degrees. The distance between an oxygen, a hydrogen, and water is 0.958 angstroms. And we have here what are called van der Waals radius. That's just basically like a hard shell. Due to the electrostatic forces of the nucleus and the electrons surrounding the nucleus, you can think of the van der Waals radius as no other atom can enter this due to electricity. So that's all a van der Waals radius is. Now, with the shape and electrostatics of water, that is partial positive and partial negative, water has some very interesting properties. And these properties are all basically due to hydrogen bonds. Shown here in this image is a hydrogen bond, and we usually show it through dots or dashes. Here we have the hydrogen of one water, hydrogen bonding with the lone pairs of oxygen of another water. And in general, we can determine if something is hydrogen bonding through distance and through bond angles. So I'm just going to talk about distance right now because that's the easiest to understand. And generally, the distance between a hydrogen and the heavy atom it's bonding with, so in this term oxygen, is roughly 1.8 angstroms. And an angstrom is a common measurement in biochemistry. It's 1 times 10 to the minus 10 meters. So it's very small, 0.1 nanometers. And in a hydrogen bond, if we look at just heavy atom, it's 2.6 angstroms. And when I say heavy atom, a heavy atom is basically anything that's not a hydrogen. Now, these hydrogen bonds are really weak. If you compare a hydrogen-oxygen hydrogen bond to an oxygen-hydrogen covalent bond, the hydrogen bond is about 1/20th the strength of a covalent bond, so extremely weak. And talking about hydrogen bonds in general, the only heavy atoms that can hydrogen bond are oxygen, nitrogen, and fluorine. Carbon can never hydrogen bond, and I want you to remember that right now. I see this mistake all the time. There's going to be a question on the test about this to see if you have it, so just keep this in mind right now. Carbon and hydrogens attached to carbon can never be in a hydrogen bond. Only oxygen, nitrogen, and fluorine. Talking about water some more, let's talk about ice. And ice is a solid structure, and the strength for the structure comes through hydrogen bond. So in ice, you have water molecules that have their maximum number of hydrogen bonds, 4 each, 2 for the oxygen and 2 for the hydrogen. And when this happens, you form a crystal lattice structure as shown here. So ice is just a repeating structure of hydrogen bonds. And so when ice forms, you have these 4 hydrogen bonds, and in water you roughly have 3.2 hydrogen bonds. What that means is that some water molecules have 3 and some water molecules have 4 hydrogen bonds. So since ice has the maximum number of hydrogen bonds, the water molecules actually spread out. Since these water molecules spread out in ice compared to liquid, ice is less dense than water, and ice will float. This is extremely important for life on Earth since we have big water oceans. If ice was more dense than liquid water, what would happen is that ice would go to the bottom of lakes, and you'd freeze from the bottom to the top, and basically life would probably never happen. Luckily, water is most dense at 4 degrees centigrade, so that means ice floats and the bottom is still liquid water. Talking about hydrogen bonds, it is much easier to melt ice than it is to boil water. And the whole reason for that is breaking hydrogen bonds. So like I said, you go from ice to liquid water, you're losing maybe a hydrogen bond. That takes 6 kilojoules of energy per mole of ice. While if you're going to boil water, you're breaking every single hydrogen bond in water to make it a gas. That takes a lot of energy. So that's roughly 41 kilojoules per mole. So that's why if you have a block of ice on the stove, that block of ice is going to turn to water much faster than it will turn to gas. Speaking of liquid water, we have ice having a crystal structure, but what happens in liquid water, since water is constantly moving, that is rotating and translating, in fact it changes its orientation every 10 to the minus 12 seconds, you have these local networks of rings. So you have these local networks of hydrogen bonding rings that are more or less being broken and form extremely rapidly. So water constantly moving, constantly breaking and forming its hydrogen bonds. And now let's think about water in conjunction with what we talked about in the last couple of videos, energetics. So let's think about the energetics of melting water, going from ice to liquid. We look at our free energy equation, delta G equals delta H minus T delta S. For this to be spontaneous, remember delta G has to be negative. So when we melt water, we are breaking hydrogen bonds. If you break a bond, enthalpy is positive. While going from ice to water, you're going from a crystal structure to these free changing moving structures. That's a lot more chaotic. So entropy increases as well. So if delta S is positive here, that means minus T delta S is negative. And so water melts at 0 or 273 Kelvin because at that temperature the minus T delta S is bigger than your positive delta H, making your overall delta G negative. And we'll look at delta G equations in class so you can get a better hold of that concept. And that's it for this video, and I will see you in the next video.